Let's go to the first metric function. We will select cells where I want to display the result. Then I will press the equal sign and choose the first range of the first metric. Press plus sign in the second range of the second metric. After that, press the enter and I will get the result. Next, we move to the next metric function. We will select the range of the cells where we want to display the result, and then press the equal sign to begin entering the formula in Excel. Highlight and select the entire first matrix range. Press the minus sign and select the second matrix range. Then press enter. We will get the result of the matrix subtraction. We will multiply the matrix by a number. First, we will do the same steps as before. Highlight the cell range where we want to display the result. Then press equal sign to begin entering the formula in Excel. Next, we will highlight the range of the matrix we want to multiply. Press asterisk, the multiplication symbol, and enter the number we want to multiply by. After that, press enter and we will get the resulting matrix. In this case, we multiply two matrices. We will no longer do it manually. Instead, we use an Excel function. Since there are two 4x4 matrices, the final matrix will also be a 4x4. First, we select all the cells where we want to show the result. Press the equal sign and enter the formula. And then specify array 1, meaning the first matrix. Type a comma and then select the second matrix. After that, we close parentheses and press enter, and then we will get the result of the matrix multiplication. This requires a square matrix. We will select a cell for the result. Press the equal sign and then enter the formula. The array is the matrix we select for which we want to commute the determinant. After typing that formula, we highlight the matrix we want to take the determinant of, close the parentheses and press enter, and then here we are the result. First, we will select the cell range where we want to display the result, and then we press the equal sign and enter the formula, the function in Excel, minverse. For the array, I will select the matrix range, close the parentheses, and press enter, and then we get the inverse of that matrix. Since this is a 4x5 matrix, after transposing, will be a 5x4. I will highlight the result cells, press the equal sign and enter the function transpose. For the array, I will select the original matrix, close the parentheses and press enter, and then we get the transposed matrix. We will form a matrix with the coefficients in front of the variables and then multiply these coefficients by x, z, y, and t. This will equal the corresponding constant terms. In order to find the solution of x, y, z, and t, we will use the formula x equals the inverse of matrix A times matrix P. First, we will calculate the inverse of the matrix A by using the minverse function. After that, we multiply this inverse matrix by matrix B using the mmut function. We select the result range, enter the formula, multiply the two matrices, and press enter. We get the solution for x, y, z, and t as 1, 2, -1, and 5. Given a market with 4 interdependent commodities having the following supply and demand functions, we set up a matrix where each row represents a function. For example, we have 4 equations: supply 1, demand 1, supply 2, demand 2, and so forth. The requirement is to construct the matrix and determine the equilibrium prices and quantities for all 4 commodities. In other words, we form a system of 4 unknowns. After setting the supply equal to the demand, we get a system of 4 equations. Then we will commute the determinant of that coefficient matrix. The determinant is formed by the numbers in front of the unknowns, the variables. Its element in the determinant is commuted using the inverse function. After selecting the matrix, we will commute the determinant. I do this for each of the 4 equations. After we have all the 4 determinants to find the equilibrium price factor, we take each determinant and divide it by the total. In this way, we select the ratio of each determinant, and thus we get the equilibrium prices. We repeat it for all 4 equations, and we will have our 4 solutions. There is a technical coefficient matrix A, assuming a market with 4 sectors. The corresponding values are given in the matrix along with the final demand matrix B. The problem requires us to find the total output matrix, which is X. To find X, we first commute I minus A, where I is the identity matrix, using matrix subtraction. As shown earlier. Next, we find the inverse of I minus A by using the inverse function in Excel. After obtaining the inverse of I minus A, we calculate X by multiplying the inverse of I minus A with the matrix B using the mut function. And then finally, we obtain the result.
For the Requirement 1. Apply models that use matrix knowledge. We will dive into economic model applying matrix knowledge. The essence of the input-output model. The input-output model was developed by economist Vasily Leontief. The core of this model lies in viewing the economy as a closed system in which industries are closely interdependent. The output of one industry becomes the input of another. And what can the input-output model be used for? For example, the steel industry requires electricity for smelting, while the electricity sector needs steel to build power plants and transmission infrastructure. Measuring this interconnection allows us to see the overall picture of the entire economy rather than looking at each industry in isolation. For the formula, we have X equal A multiplied X plus B, where X is total output vector of all industry. A is technical coefficient matrix. Each Aij shows how much output from industry I is needed to produce 1 unit in industry J. Ax is intermediate consumption, inter-industry transaction. B is final demand vector, household government. To determine the level of total output needed to satisfy a given level of final demand, we can transform the equation to this formula. Next, applications. The model is used to determine production levels that meet demand while minimizing inventory costs. It ensures no shortage for both inter-industry and external market demand. It maintains optimal balance. Either inventory is fully used, zero leftover, or no new production occurs if existing inventory is sufficient. Alternatively, we can say the input-output model is a powerful tool for planning and forecasting. Production planning, it can answer questions such as, if the government increase final demand for agriculture products by 20%, how much total output must related sector like fertilizer, machinery, and transportation produce to avoid supply chain disruption? Impact analysis. It measures the ripple effect of economy shocks. For example, a sudden increase in energy price. An input will spread through matrix A, raising production costs across all industry proportionally. Next, we will have the market equilibrium matrix. The definition of this is a mathematical tool that uses linear algebra to determine equilibrium price and quantities in models with multiple interdependent goods. The meaning of this is using matrices instead of solving individual equations provide the following advantage. Interdependence. Goods are not independent. For example, an increase in fuel price affects car demand and transport supply. System-wide view analyze the entire economy or sector as a unified system rather than in isolation. Stability analysis. Using determinants, we can determine whether a unique and stable equilibrium exists. Application for this is macroeconomic analysis, which is used in the input-output model to forecast industry outputs needed to meet total demand. Substitute and complementary goods analysis evaluates how price change in one good affects another. Example, pork, beef, printer, and ink. Finance and investment helps determine equilibrium in capital market, saving versus investment, predicting interest rate, supply chain optimization, balance production capacity and demand across location to minimize inventory and transportation costs. Next, we'll get to know all the real-life application models that use matrix knowledge. We have simple additive weighting, or we can call it SAW, also known as the weighted sum method, is a technique in multi-criteria decision analysis. It determines the overall score of an alternative by summing the products of normalized criterion scores and their corresponding weights. This is the most commonly used method due to its simplicity, intuitiveness, and ease of explanation for non-experts. The core idea of SAW lies in the concept of compensation, quantifying different values. It allows comparison of criteria with different units. For example, price versus satisfaction by converting them to a common scale. Trade-off an alternative that performs poorly on one criterion. For example, higher price can still be the best choice if it scores very highly on another important criterion, like excellent quality, to compensate. Objectifying preference. It forces decision makers to clearly assign importance to each criterion through weights rather than relying on subjective or impulsive judgment. For example, you want to choose among M alternatives, example like 3 jobs, based on N criteria, salary, environment, or location. We have the score matrix has a size M multiply N. Each row presents an alternative, and each column represents a criterion. The weight vector W size N multiply 1. It contains the importance priority assigned to each criterion, which the following formula V equals S multiply W. We can expand it like this. For applications, SAW is widely applied in any field that requires choosing the optimal option amongst multiple alternatives. Human research management, evaluating and ranking candidates based on criteria such as experience, soft skills, expected salary, and test results. Supply chain management, selecting the best supplier based on price, delivery time, reliability, and product quality. Investment and finance, assessing investment projects or stock portfolio based on expected return, risk level, and payback period. Personal life, choosing a house, car, or university by comparing location, cost, facility, and brand reputation. Government and public sector, evaluating public procurement projects or selecting locations for infrastructure development.
So now we're moving to the linear programming, which is an important optimization method. So for the first part, we will be learning about the general concept of linear programming. The first one is definition, and the second one is the forms of linear programming problems. For the definition, so what is linear programming? Linear programming is a field within linear optimization that studies how to find the maximum or minimum value of a linear function, which is the objective function, subject to linear constraints. The linear programming have two parts. The first one is objective function, which represent the profit, cost, or output. And the second one is constraints, is the condition that limit resources. For example, linear programming can be used to determine the maximum profit or minimum cost of a business, modeled by a function of multiple variables. So for example, if a sweet factory wants to calculate its cost, it should be rely on the limit resource of sugar, flour, and such ingredients.
Moving to the next part, a linear programming problem includes an objective function and set of constraints, and it has three forms to represent the function: general, canonical, and standard. The first one I'll be introduced is the general form. As you can see, this is the general form of the objective function of linear programming problems, in which C is the coefficient of the objective function, and X is the decision variables that we are looking for. Moving on, the linear programming problems has its constraint like this, in which A and B are coefficients of the constraint. At that point, X vector presents a solution set that satisfies the constraint is called a feasible solution of the problem. A feasible solution is that satisfies constraint at which the objective function attains its minimum or maximum value over the set of feasible solutions. It's called an optimal solution of the problem. Solving a linear programming problem means finding an optimal solution, or showing that the problem has no solution. That means it has no optimal solution.
So the next one is canonical form. The requirements of canonical forms are all the constraints have to be equations. So it is not in equations, and all variables are non-negative. So its variable should be greater than 0. And this is the linear programming problem in canonical form. So as you can see, the linear programming problem in canonical form is just a special case of the general form, where all constraints are equations and all variables are non-negative, because its form is the same, but the difference is in the constraints. We have the standard form. The linear programming problem in standard form is a canonical form problem where all right-hand side constraints are non-negative, and the coefficient matrix contain m unit column vectors. And for that, the basic variables is the variable that corresponding to unit column vectors, and specifically the variable corresponding to unit vector EK. And a solution in which all basic variables are 0 is called a basic solution. This definition will help us in calculating the solution for the math problem that I'll be showing later. A basic solution with exactly n positive components is called non-degenerate. Otherwise, if it was fewer than n positive components, it is called degenerate.
Then we move to the part called converting from standard form to canonical form, because the constraint of standard form is written in equation, while canonical form is written in equation. So if you want to convert a problem in general form to canonical form, there are two situations. For the first one, if the constraint is written in the form less than or equal to, we add a slack variable s. In contrast, if the constraint is larger than or equal to, we minus the slack variable s. For example, this problem is written in general form and the equation is smaller than or equal to, so we'll add s to both constraints. And this is the new constraint that we have in canonical form. For example, a company produces two types of food products, X and Y. The production requires three types of raw materials: flour, sugar, and vegetable oil, with available amounts of 15 tons, 12 tons, and 10 tons respectively. To produce 1 ton of product X required 0.5 tons of flour, 0.5 tons of sugar, and 0.2 tons of vegetable oil. 1 ton of product Y requires 0.6 tons of flour, 0.3 tons of sugar, and 0.5 tons of vegetable oil. The selling price per ton of product X is 100 million Vietnam dong, and product Y is 112 million Vietnam dong. So the question is, how many tons of each product should be produced to maximize revenue?
So to approach the solution, we let X and Y be the number of tons of products X and Y produced, respectively. So the first thing we will do is to write the function fxy representing the total revenue in terms of X and Y. Then we will form a system of linear inequalities in two variables X and Y, and we will graph the feasible region of the system. And then we will determine the coordinates of the vertices. Then we will determine the coordinates of the vertices of the feasible region and compute the value of fxy. So as you can see here, this is the table that I have written out. We have for each amount in tons for product X, we need 0.5 flour in ton. So the total flour should be 0.5 multiplied by X, and the total sugar is 0.5 multiplied by X. The total oil is 0.2 multiplied by X. For the same concept, the total flour in tons for product Y, also written at 0.6 multiplied by Y. Sugar is 0.3 multiplied by Y, and oil is 0.5 Y. So we have the objective function, which is the total revenue for this problem. We have 100x, means that 100 is the price of X, and X is the amount in tons, and 112y plus 112y. And the constraint of the problem is the limited resource of flour, sugar, and oil that the problem gave. So the amount of flour that we use have to be smaller than or equal to 15. The amount of sugar have to be smaller than or equal to 12. And the amount of oil have to be smaller than or equal to 10. So next, we'll graph our inequation. This is the inequation that we recently made. And we notice that all the ingredients have to be smaller than or equal to 3 of this number. So the region that we're finding belongs here. So next, we will determine the vertices A, B, C, and D. And also we have the point of 0 and 0. Okay, so this is the value of 5 of the points. We can calculate this value by finding the intersection of two random inequations. Okay, so as we have 5 of the value set, we will substitute it into this function. For this is the solution that we ended up with. So we can notice that this C solution is the biggest one. So by that, the revenue reaches its maximum at point C. So that means the maximum revenue reaches when producing 18 tons of product X and 10 tons of product Y, given the available resources. So the next method that we'll get to know is the simplex method. So this simplex method that I'll be showing you today is only it only can apply in standard form. So the first step, we have to check the constraint matrix to ensure the problem is in standard form. And then the second step, we will identify the basic variables. The third step is to construct the initial simplex tabular. To draw the simplex table and fill in the following components of the standard form problem. For the row 1, we will list all variables of the problems, including slack variables. For the row 2, we will write the coefficients of variables in the objective functions. Column 2 is the basic variables. Column 1 is the corresponding coefficients of the basic variables. Column 3 is the constant terms of the main constraint system from top to bottom. And the last column, which is column 4, is to write the constraint matrix A of the problem. So the fourth step is to compute the reduced cost, and also called the evolution of coefficients delta J of the variables. Okay, so we'll move to the example and we'll solve this math problem together. So this math problem is a standard form problem, and they ask us to find the max, so it's the maximization problem. So the condition for a maximization problem is delta J larger than or equal to 0 with all x and j from 1 to n. So the first one we'll do is we'll build matrix A. So as you can see, this value in matrix A is the value of the coefficients in the constraints. So as we write this matrix A, we can notice that this x1, x3, and x6 is the basic variables because it's written in this form of only 0 and 1. Then this is the table that I have built. We have the basic coefficient column, the basic variable column, basic feasible solution column, and this is the variables that we are finding. Okay, so for calculating this final row, which is the delta J, first of all we can notice that this x1, x3, and x6 is the basic variables, so they are all 0. So to calculate this value, we will take 2 multiplied by 6 plus 4 multiplied by 2 plus 0 multiplied by 3. We will have, so 2 multiplied by 6 is 12 plus 4 multiplied by 2 is 8, and then we have 20, and for the 20 we will minus 5. So that means we have 25 in solution. Yeah, so we'll do the same thing for this value and this value. Okay, so as we notice, the optimal condition for the maximization problem is that delta J larger than or equal to 0. So this x1, x3, and x6, they are basic coefficient, so they absolutely be 0. So we don't calculate that. For this problem, we can see that 0 is the smallest value that satisfies the condition, so we will take this value of 0. Okay, so the optimal solution of the set, this is the vector of the optimal solution. So by that, x1 is 32, x2 is 0, x3 is 30, x4 is 0, x5 is 0, and x6 is 36. So 32, 30, and 36 is the basic coefficients, and we keep only this 0 from the x5 because it's the smallest value that satisfies the conditions. And yes, and then we substitute this into the target. So we will substitute this set into the functions, and then we have the z max of 184. However, this optimal solution is not unique, means that there is not only just one set of solution, because there exists a non-basic variable whose reduced cost equals 0, which is x5. Therefore, we can find another optimal solution by choosing x5 at the entering variables. But we'll not be doing it here because we has find our target solution of 184. I will brief about the next step we can do to find another optimal solution. So we already have the optimal solution of 184, but it's not unique. So another optimal solution can be obtained by choosing x5 as the entering variable and performing one additional simplex pivot. That also marks an end for our presentation. Thank you for your listening and for your watching.